Thanks for the introduction, Beth. So, like she said, my name's Cecile Grub, and I work for the engineering department up at Western Washington University. I don't know that all of you know that much about Western Washington University. We're up in Bellingham, Washington, up in the top left corner of the state. Our engineering program is undergraduate only. We've got 5 different tracks in plastics and composites engineering, manufacturing engineering, electrical engineering, vehicle design, and industrial design. And I work for the plastics and composites program. And we've got some curriculum in advanced composites, thermoplastics, polymer chemistry, materials characterization, manufacturing, and just a bunch of stuff that's really important to the aerospace industry. And one thing that we're really proud of at Western is our primarily industry-sponsored research. So we like to talk a lot about how we have real-world, hands-on problems for our students. And I'll go into that a little bit later when I talk about the research problem we worked on. But first, a company that you probably are more familiar with than Western, which is Zodiac Aerospace. They're a world leader in aerospace equipment and systems for commercial, regional, and business aircraft. We work mainly with their Washington branches and some of their California branches, but they've got 100 locations worldwide and 35,000 employees. So they're pretty important to the aerospace industry, but they're also really important to us because they employ a lot of Western grads, not only from my program, but from the manufacturing program as well. So a little about our partnership. We started working with Zodiac back in 2012, which coincidentally was when Ducati was just starting up. So the first project that we did with Zodiac was investigating a problem they were having with composite panel warpage, and that was the first grant that we received from Ducati. We've started working on some different stuff since then, which is mainly focused on developing new materials for the aerospace interiors industry. But we've been very grateful to Ducati for the support from 2012 and onwards. A little bit about the partnership. I think both of the groups would say that the partnership is really mutually beneficial. Zodiac gets access to facilities and expertise in areas that they don't otherwise have access to and lets them do a really wide range of research. Well, we're really grateful for the opportunities to provide our students with a more comprehensive education and, like I said, access to real-world problems for senior project capstones, but for research projects that involve students from the sophomore level onwards. So, specifically the problem that I'd like to talk about today that's involved with transitioning technology to industry was solving this problem for Zodiac, which was that they needed to qualify a new material supplier for phenolic prepreg, which, for those of you who aren't familiar with prepreg, it's a fabric that's been pre-coated with a thermosetting resin. So they had completed standard quality control tests like resin content, volatile content, resin flow, and a host of mechanical testing methods. But they really needed to know more about how the degree of cure of the two materials compared. And to understand why that's important, I want to talk a little bit about the prepreg manufacturing process, which really happens in 3 stages. The first stage, or the A stage, is where the fabric is coated with the thermosetting resin, and you can see that all the way on the left. After that, it's heated in an oven system, and B stage are partially cured or partially cross-linked, at which point it's prepreg. And the degree of cure at this stage is really important to the final stage, which is the composite parts that you find in your aircraft, because it affects how the material molds and the mechanical properties and the physical properties of the final part. So, like some of you probably know, there's a standard method for measuring degree of cure, which is using differential scanning calorimetry. It's the ASTM method, and it works really well for things like epoxies. So DSC measures the heat flow of a material over a range of temperatures, and if you integrate the temperatures or the heat flow while a material is curing, you can infer a degree of cure from that material. And so you can see the standard DSC results for an epoxy or that sort of resin on the right You can see what the DSC of phenolic resin looks like on the left, and it is not very pretty, and it's hard to integrate, and it really doesn't work. So using knowledge that we'd gained all the way back to 2012, we came up with a new approach, which involved manufacturing prepreg at Western using our laboratory scale prepreg treater, which we built using Zodiac and Ducati funding. And we used it to manufacture prepreg at a variety of temperatures to get a variety of different levels of cure. And then we investigated the level of cure using a bunch of different methods, including some specialized DSC, DMA, and gel permeation chromatography. The solution that we came up with was using gel permeation chromatography, which allows you to analyze the molecular weight of a polymeric material. And what's cool about this is that unlike DSC, it's applicable to pretty much any commercial resin system, including solvent-based systems like phenolic. What else is cool is that Zodiac has GPCs, so they were able to take this method that we have developed and implement it immediately just using the procedures that we came up with. So we were pretty proud of that. And one thing that's cool is that we were able to do this over the course of 3 months. So Zodiac came to us with the problem, we worked on it for summer, and by the end of the summer we had a solution. And I guess I meant to talk about this more on the next slide too. Not only did we come up with a solution for Zodiac, but it allowed us to better qualify the research machine that we built, which has been really beneficial to us going forward with our research. So to kind of wrap this up, I'd like to talk about what I think the benefits of the Ducati partnership are. So like I mentioned before, our students get access to these really cool projects that let them interface with industry professionals. And it's really cool to see the ones who start as sophomores or juniors grow throughout their education and become much better at presenting and at the soft skills that engineers don't always get. For us, it's really, the Ducati program has really improved our connections with Zodiac, because allowing us to leverage both those funding sources has just allowed us to do a lot more research. And then for Zodiac, this program has allowed us to do research in a lot of areas that we wouldn't have been able to otherwise. And like I was saying before, it's really decreased the amount of time that it takes us to solve these problems. So 3 months without Ducati's funding would have been multiple years, because we wouldn't have had the prepreg treater or that equipment that we were using to analyze the material. So finally, I'd like to acknowledge a handful of people, some of which are in this room. At Western, Nikki Larson, Mark Perrin, and John Masasi, as well as students Mark Seeley, Gunnar Linskog, and David Peoples. At Zodiac Aerospace, Jim Del Pinto has been extremely helpful to us over the years, as well as Kevin Bussard and Kevin Korf. And last but not least, I'd really like to give a shout out to Beth Hacker for keeping the Ducati program alive and prospering. So thank you.